or prices. They could also be about quality of their product, as in the problem set. More broadly, you can think about anything as being a strategy and a strategic interaction you have with. So like, who you date, where you eat might depend, all these things might depend on what other people are doing. And the participants' payoff, how well off you are, depends on how other people do. My profits depends on how much you produce. And actions are taken simultaneously, as in Cornell. If actions are taken simultaneously, as in Cornell, we call the game a normal form game. A normal form game is one where we all simultaneously choose what we're going to do. Or actions can be taken sequentially. I can do something, and then you get to choose after me, and that's called an extensive form game. So Stackelberg is an extensive form game. So just like in competitive equilibrium, we need some way to think about what the solution is. In competitive equilibrium was demand equals supply. Here it's going to be, something different. And that's sort of the focus of what's called game theory, is how do we think about what firms do in situations like this. The most famous idea was from John Nash, and it was called Nash equilibrium. So Nash equilibrium is the standard solution to a normal form game where everyone chooses things simultaneously. Every player takes as given the strategy of the other players and does the best thing they can do given those strategies. And the strategies are not really what the players are choosing, but rather what they're taking as given that the other players are choosing. And so, for example, in this case, the intersection of those reaction curves was exactly the Nash equilibrium. It was what I want to do given what the other person is doing, and they're doing the best thing given what I'm doing. A subgame perfect equilibrium, on the other hand, is the Stackelberg model. And the way that we solve that is by solving backwards, like we did there. We say, what would the guy who acts second do given what the guy who acts first does? And then, given that the first guy takes that into account, what's the optimal thing for him to do? Right? So chess is an example of a normal form, of a sequential game, which you can solve by subgame perfect equilibrium as well. So you could think, what are all the possible end moves of chess? Right? What would everyone do before those? What would everyone do in the step before that? What would everyone do? So you can, in principle, solve this by backwards induction. Now the problem is, there's so many different arrangements of the chess game that you can't possibly do that, and that's why no computer can absolutely reliably beat a human being in chess, but in principle you could do that. And the key idea here is that the first player anticipates the effect that his action has on what the action of the next player is doing. So, we won't use this much in the course, but it's a broadly used idea. Okay, so now that we have this broad idea of an equilibrium, the key question is going to be, what do firms take as the other firm's strategies? What do they take as fixed or given when they make their decisions? And what do they think might change when they make their decisions? So we assumed that firms took as given the other firm's quantities. Well, why should we do that, right? It's not necessarily obvious that firms think that other firms will leave their quantities fixed when it chooses its quantities. In fact, they might think other firms will leave their prices fixed when they change their quantities. And this makes a huge difference. So this was the argument given by Bertrand and Edgeworth. And they considered several firms with identical common marginal cost, each which takes as given the price of the other firms. So, Justin? Is Justin here? Does anyone else want to try to describe what a Bertrand equilibrium would be like? What would be the equilibrium in this game, or how do you imagine it going? Well, imagine that prices were anything above cost, right? So imagine some firm is making profits, right? Well, then another firm could come in and just charge slightly less than them and take all of the business in the industry, right? And take all of their profits, right? So clearly they're going to want to do that, right? Because if one firm's making profits and another firm's not, they're going to want to undercut the other firm by a little bit. But then the other firm is going to want to say, hell no, I'm not going to let you steal my market. I'm going to undercut you by a little bit myself, right? And on the other hand, if any firm is losing money, they're clearly not going to want to do that, so they're going to want to raise their price, right? So the only thing that could ever be in equilibrium is where no one's making any profits, right? So everyone's charging price exactly equal to cost. So this is called Bertrand and Edwards paradox. As long as there's more than one firm, the only equilibrium is price being equal to cost. Yeah.
Does it matter if they're producing at different quantities? Because their marginal costs will be different. So
Well, no, they all have the same marginal cost.
But at different quantities, they'll be at a different point on their marginal cost curve. So
No, sorry, they have constant marginal cost equal to C. All the firms have constant marginal cost. It's also true that the firms are, no matter what you have, that this is always going to be the only equilibrium. But anyways, yeah. So, this seems a bit implausible because what it requires is that if I reduce my price by a tiny bit below you, I'm able to steal everyone who's buying your product. And that just doesn't seem likely to be the case in the real world. And Calvin, what are some of the reasons why you think that this might be sort of unlikely to happen?
It wasn't something like what we did in the Paulton said. Like you have to assume that the product is homogeneous.
Yeah.
In order for you to undercut to steal everything just by undercutting.
Yeah, so if Coke reduces its price by a tiny bit below Pepsi, there's a lot of people who are going to keep buying Pepsi, right? Exactly. So that's one of the most common responses. So, non-price characteristics of the products matter to people, right? Pepsi doesn't taste exactly the same as Coke. It doesn't come in the same cans. It's not sold at the same places, etc., right? Or, it could be that the products are completely identical. Like, I don't know how many people went to the John Levin talk, but even for products that are completely identical, people actually have to, look for the product, right? And so if someone else reduces their price by a little bit, it's not like everybody's immediately going to know that. They actually have to go search around and try to figure out what the prices are, right? So one way we can summarize both of these types of effects is that the amount that the firm sells will depend on its own price and on the prices of the other firms, right? And each is a monopolist on their own product, but the other products are substitutes for their product in the sense that when the other prices increase, their quantity will increase. So this is a very broad model, and we could choose to either take the quantities or the prices as given as the strategies in this model. But the one that's become most popular or common is the Nash and Prices model, or Bertrand model in this case. And because there's differentiated products, because consumers don't view all the products the same, this is typically called the Differentiated Products Nash and Prices model, or DP-NIP. Not very elegant acronym, but it's tough. Okay, so let's go back to the hoteling model that we discussed the other day, and now think about the firms having their locations fixed, but choosing prices, right? So imagine that the two firms are at the ends of the hoteling line. One is at 0 and one is at 1, right? Now, consumers are going to choose to buy from firm 0 if the total cost to them, both from getting there, which is the transportation cost, right? If I live at X and I want to go to 0, it costs me the transportation cost T times the distance X, right? Plus the price that I have to pay to buy the product, right? And I'm going to buy that exactly if that is less than the cost that it takes me to move to 1, which is 1 minus X, right? Times the transportation cost, plus the price that I have to pay if I buy it at 1. Okay, so Botow?
Oh, okay.
Hey, Botow. So what is going to be the cutoff X such that I am going to go to buy it from 0 versus buying it from 1? Obviously, people who live really near 0 are going to buy from 0, right? People who live really near 1 are going to buy from 1. But what's going to be the point of where people to the left of it versus the right of it will...
You said this inequality equal.
You can solve on the board if you want. Yep, so solve for the X point at which people are just indifferent between the two. Great. Great, so that's exactly right. And what that says is that the higher that that firm 1's price is, the more people are going to buy from firm 0, right? The lower firm 0's prices are, the more people are going to buy from firm 0, right? And then it'll depend on the transportation costs as well. So what this means is that if the number of people is uniform over the interval, right, then the demand is just going to be P1 for sorry, this should be Q0, P0, P1, so just subtract 1 from those ones there, sorry. So Q0 is going to depend on the two prices, and it's going to decrease in the price of firm 1 and increase in the price of firm 2, but it's not going to do so discontinuously like in the Bertrand model, right? Because some people have to travel further to get to firm 0, and some people have to travel further to get to firm 1, right? Okay, so this is just exactly linear demand, right? And imagine that the cost of production is 0. What is going to be the optimal price for the firm to set? Rian? Yeah. Rian, you can come solve on the board, or can you come, don't look at the slide. So if there's no cost of production, what's the firm's profits? Again, 0, 0, 1. No, that's if it charged price is 0, but what's its profits as a function of the price P0 that it charges? So if it charges price P0, and this is the amount that it sells, what's its profits? No, it's the price times the quantity, right? If it charges price P0, and this is how much it sells, right? Yeah, so what's that? So you can take the derivative of that, or do you remember the trick that we have when there's a linear demand? What's the optimal price for you to charge?